Welcome back to the deep dive. Today, we're diving into something that honestly sounds a bit like science fiction, doesn't it?
It really does.
Can a living plant, like the one on your desk, actually generate enough power to charge your smartphone?
It sounds completely wild, but the science is surprisingly real. We're talking about bioelectricity today, or maybe more specifically, plant microbial fuel cells.
Plant microbial fuel cells. Okay.
Yeah, and it's not just some lab curiosity. People are calling this a potential technological revolution. The idea that, every houseplant, every wetland could quietly be generating clean power.
It's a huge idea. We've gathered quite a bit of research on this, looking into this eco-technology. So our mission today is to really get under the hood.
Right.
How do plants actually help make usable electricity? How does the science capture that? And importantly, what are the real-world limitations right now? Let's unpack this.
Okay. Well, the first thing to get is that bioelectricity isn't something we invented. It's something we learned to harness. Every living thing, plants included, generates tiny electrical signals. It's just part of being alive, but harnessing it efficiently. That's where these microbial fuel cells, the MFCs, come in with plants.
So it's not like the plant leaf itself is suddenly a solar panel. It's more complicated than that.
Exactly. You can't just stick wires in a potato and hope for the best, not for continuous power anyway. What's really fascinating here is the plant isn't the battery itself.
Okay.
The plant is more like the engine, or maybe the fuel provider for the battery. It's a team effort. Plant, soil, and crucially, microbes.
Microbes. Okay, tell me about that part.
So everyone knows photosynthesis, right? Plant takes sunlight, water, CO2.
Makes sugars, glucose.
Right, glucose. That's its food. It uses maybe half of that to grow bigger leaves, stronger roots, all that.
And the other half?
That's the key. Up to 50%, sometimes even more. It just releases through its roots.
Into the soil. Water.
It's organic waste, basically. Things it doesn't need. Think of it like organic runoff.
So the plant is constantly leaking food energy into the ground around it.
Precisely. And guess who loves that waste?
The microbes you mentioned.
Exactly.
Yes.
Specific types of bacteria that naturally live right there in the soil around the roots. Scientists call that area the rhizosphere.
Rhizosphere. Got it.
These microbes chow down on that organic stuff. They metabolize it, break it down, oxidize it, technically. And in that process...
Let me guess. Electrons?
Bingo. They release electrons, free electrons just floating around in the soil thanks to these busy bacteria.
Wow. Okay. So the plant's waste feeds the microbes digest it and release electrons. That's where the electricity originates.
That's the source current, yes.
Okay, here's where it gets really interesting then. How do we grab those electrons? You need hardware for that, right? You need a circuit.
You do. It's actually pretty classic electrical principles. You need an anode and a cathode. You place them right there in the soil.
Like little energy catchers?
Kind of. The trick is placement. These electron-releasing microbes, they thrive without oxygen. They like it anoxic.
Okay, so deeper in the soil, near the roots.
Generally, yes. That anoxic zone is where you put the first electrode, the anode. Its job is just to collect all those electrons the bacteria are shedding.
Makes sense. So the anode collects the electrons. What about the cathode?
The cathode goes closer to the surface, where there is oxygen. Lots of it.
So you have a zone without oxygen for the anode and a zone with oxygen for the cathode.
Exactly. You create a potential difference. Then you just connect the anode and cathode with a wire externally.
And the electrons want to move?
They sure do. They flow naturally from the electron-rich anode through the wire to the electron-hungry cathode where they react with the oxygen. That flow is your electric current.
So plant makes food waste, microbes eat the waste, release electrons to the anode, oxygen at the cathode, pulls the electrons through the wire, and it just keeps going.
As long as the plant is alive, photosynthesizing and feeding those microbes, yeah, it's a continuous self-sustaining little power source.
That's genuinely amazing. It's tapping into a natural cycle without, hurting the plant.
That's the beauty of it. Ideally, we're harvesting energy from a waste stream. We're not cutting leaves or damaging roots. It's incredibly sustainable in principle.
Okay, but let's hit the brakes for a second. Voltage, you said tiny electrical signals earlier. How tiny are we talking?
Very tiny. Millivolts per square meter of plant. Maybe up to 0.5 to 1 volt from a single small setup, if you're lucky.
Right. So nowhere near enough to charge a phone or light an LED directly from one plant pot.
Absolutely not. The pressure, the voltage is super low.
So then how did these companies in the Netherlands actually get stuff to work? Powering lights, you mentioned phone charging earlier. How do you bridge that gap?
Yeah, that raises an important question. It's all about smart engineering and scaling up, not by making one giant plant battery, but by connecting lots and lots of small ones.
Ah, like wiring batteries together.
Exactly. You use standard electrical engineering, connect them in series, you add up the voltage, connect them in parallel, you add up the current.
So you could have, say, a whole field of plants, each contributing a tiny bit.
And you wire them together into a grid. Hundreds, maybe thousands of these little plant MFC units working together. That's how you accumulate enough power for something useful.
So it's distributed generation, literally from the ground up.
Precisely. That company, Plant A in the Netherlands, that's what they do. They have these modular systems. They often put them in places that are already good for it, like wetlands or rice paddies.
Why wetlands?
Because the soil is naturally waterlogged, which means it's low in oxygen deeper down. Perfect anoxic conditions for the anode and the microbes. Maximizes efficiency.
Clever. And they have actual products, like the plant lamps?
Yep. Functional plant lamps, even modules you can put on roofs. It proves the concept works for low-power applications. It's not powering cities, but it's working.
That feels really significant, not for replacing the grid, maybe, but for localized power. Like you said, remote sensors, maybe pathway lighting in parks, off-grid irrigation sensors.
Exactly. Changes how you think about powering small things in remote or sensitive environments. No need for batteries or long wires sometimes.
And it sounds like the research isn't stopping there. You mentioned something about merging this with solar, biosolar cells.
Yeah, that's another really interesting avenue. Researchers are looking at combining these plant MFC systems with traditional solar panels.
How would that work? Putting plants under solar panels?
Sort of, yeah. Or integrating the systems.
Yeah.
The idea is synergy. Solar panels work best in bright sunlight, obviously.
Right.
But this bioelectricity process, it depends more on the plant's continuous growth and waste cycle, not necessarily direct blazing sun. It works in shade. It works when it's humid. Conditions where solar panels sometimes struggle.
So the plant power could sort of fill in the gaps when the solar panel isn't at peak performance?
That's one idea.
Oh.
Or just maximizing the energy you can get out of a given piece of land. You get solar from above, bioelectricity from below.
Yeah.
Especially useful in, say, tropical climates, often cloudy, very humid, lots of plant life.
That makes a lot of sense. And it paints a really cool picture for, like, future cities. Green roofs, living walls. They wouldn't just be nice to look at.
Exactly. Imagine if your building's green facade was actually helping to power the lights inside, or contributing to the sensor network.
It makes green infrastructure suddenly have a direct economic payback beyond just aesthetics or insulation.
Right. It provides a stronger incentive. If that green space is actively saving you money on electricity, you're more likely to build it and maintain it. It shifts from just nice to have to functional asset.
Okay, this all sounds incredibly promising, but we need the reality check now. This isn't green magic, right? There must be significant hurdles.
Oh, absolutely. I mean, we have to be realistic. This is still very much an emerging field.
What's the biggest bottleneck right now? Still the low power output.
That's definitely number one, power density. The amount of electricity you can get per square meter or cubic meter of soil is still very low compared to other energy sources.
So volume is an issue. You need a lot of space, a lot of plants connected together for significant power.
Exactly. We can power small sensors, LEDs. Charging a phone is possible, but slow. Charging your electric car, forget it. Not with current tech. We need major improvements in efficiency. Better materials for the electrodes, maybe. Better system designs.
And what about keeping the system, well, alive? You're dealing with living plants and microbes.
That's the other huge challenge, preservation. Remember, the whole thing relies on that delicate ecosystem in the rhizosphere.
Right, the plant roots, the bacteria.
If the technology we install harms that ecosystem, the power stops. If the electrodes corrode and leach nasty stuff into the soil, you kill the microbes, maybe the plant. If the physical structure interferes with root growth, game over.
So you need electrodes and systems that are super efficient at collecting electrons, but also completely non-toxic, non-invasive, and incredibly durable.
Pretty much. They need to last for years, ideally, sitting in wet soil, surrounded by biological activity, without breaking down or causing harm. That's a big ask for material science.
And it has to be cheap enough to deploy widely.
That too. Cost is always a factor. Making highly efficient, biologically inert, long-lasting electrodes cheaply and at scale. That's a major engineering and manufacturing hurdle we still need to overcome.
Okay. So bringing it all together, let's loop back to that first question we asked. So what does this all mean? Can plants really charge your phone?
The bottom line, based on everything we're seeing, yes, it's possible.
But with big caveats.
Definitely. You need the right setup, that plant microbial fuel cell system, and you need patience. It's not going to be a fast charge. It's more of a trickle charge, accumulating power over time.
Right, so it's a small spark today, but the potential, that seems to be the real story here.
I think so. The significance isn't really about replacing our current grid tomorrow. It's about demonstrating a fundamentally different way to generate power. Truly sustainable, using natural waste, perpetually renewing itself as long as the plant lives.
We've basically figured out how to plug into the Earth's own metabolism in a way, using its waste products.
That's a good way to put it. And doing it without, in theory, causing harm. That's revolutionary thinking right there.
It really is. And that leaves us with a pretty provocative thought, doesn't it? For centuries, we've built massive centralized power plants, huge infrastructure, long transmission lines, often with big environmental costs.
Standard model.
But what if this hints at a totally different future? Not centralized, but massively distributed, billions of tiny biological power generators just working away quietly underfoot in parks, gardens, farms, wetlands.
A network of living power cells.
Yeah, a truly distributed, maybe even autonomous power network integrated right into the landscape, moving from one huge power station to countless tiny living green ones. If that scales up, well, that changes everything.